For centuries, mathematics has evolved as a discipline for uncovering enduring structures and arriving at definitive answers. But is the world we live in really made up only of fixed and unchanging things? What drives reality is constant change, the relationships among different elements, and the processes through which new states emerge. Today, using the concept of transcendental functions as our point of departure, we will rethink intelligence, not as a static structure, but as a dynamic process that evolves, forms relationships, and gives rise to the next decision. From the classical world to the decision trace model of the AI era. To understand what this shift means, let us begin by looking back at how classical mathematics has viewed the world. At the foundation of classical mathematics lies the idea that the world can be described through finite relationships, from integers to fractions, and from fractions to ratios. The scope of mathematical description gradually expanded to polynomials, algebraic equations, and geometric structures. Take the square root of 2, for example. It cannot be expressed as a simple fraction, and yet, its exact value can still be defined through an equation, as the number that, when squared, equals 2, or through a geometric relationship, as the length of a square's diagonal. In this way, classical mathematics became an extraordinarily powerful language, one capable of describing shapes, proportions, boundaries, and positions with clarity, using a finite set of symbols and relationships. But not every number can be contained within such algebraic equations. So, what kind of numbers lie beyond this framework? Now, let us divide the world of numbers into three categories. First, there are rational numbers. Numbers such as 1/2 and 3/7 can be expressed as the ratio of two integers. Next, there are algebraic irrational numbers, represented by numbers such as the square root of 2. Although they cannot be expressed as fractions, their values can be defined as solutions to algebraic equations with integer coefficients. And then, there are transcendental numbers, which belong to neither category. A transcendental number cannot be the solution to any algebraic equation with integer coefficients. The important point is that a number is not transcendental simply because its decimal expansion continues forever. The decimal expansion of the square root of 2 is also infinite, yet the number can still be captured by an algebraic equation. The essence of a transcendental number lies not in the length of its decimal expansion, but in the fact that it lies beyond the classical framework of algebraic equations. The two best-known examples are e, the base of the natural logarithm, and pi, the ratio of a circle's circumference to its diameter. But why do these two numbers appear again and again across so many different aspects of the real world? The numbers e and pi are more than remarkable constants with decimal expansions that continue indefinitely. The number e appears wherever we find continuous growth and decay. It can be found in the growth of populations and investments, in radioactive decay, probability distributions, differential equations, and information theory. Whenever the rate of change of a quantity is proportional to the quantity itself, the number e naturally emerges. Pi, on the other hand, appears not only in circles and rotations, but also in waves, cycles, and oscillations. From Fourier analysis, which breaks sound and light down into combinations of waves, to quantum mechanics, pi plays a central role in describing recurring phenomena. In other words, the number e captures growth and decay, while pi captures cycles and oscillations. And many phenomena in the real world evolve as they cycle, and cycle as they change. So, what kind of mathematics do we need to represent growth and cycles as dynamic forms unfolding over time? At this point, our focus shifts from special numbers to functions that describe change. This is where transcendental functions enter the picture. The transcendental numbers we discussed earlier form a category of specific numbers. Transcendental functions, by contrast, describe processes that map changes in an input to changes in an output. Algebraic functions, such as x squared, x cubed, and the square root of x, are constructed from polynomials and algebraic relationships. They are particularly well suited to describing shapes and structures. Transcendental functions, on the other hand, include exponential functions, logarithmic functions, sine, and cosine. In general, these functions cannot be expressed through algebraic operations alone. Exponential functions describe growth and decay, logarithmic functions transform scales, and sine and cosine describe oscillations and cycles. In other words, transcendental functions expanded the expressive power of mathematics beyond algebraic functions. They made it possible to capture not only what something is, but also how it changes. To see this generative quality in its clearest form, let us begin with the exponential function, e to the power of x. A defining feature of the exponential function, e to the power of x, is that a simple rule can generate an infinite expansion. As the equation shows, e to the power of x can be expressed as an endless series. It begins with 1, followed by x, then x squared divided by 2 factorial, then x cubed divided by 3 factorial, and so on. Each time another term is added, the curve is updated and moves closer to the exact shape of the exponential function. A finite rule of generation produces an expansion without end. Even more important is the fact that the derivative of e to the power of x is simply e to the power of x itself. This means that the next change is determined in proportion to the current quantity. The result of that change then leads to the change that follows. Even as it changes, the function preserves its own structure. The exponential function represents a self-generating process in which the present state gives rise to the next. But what happens when change does not grow in a single direction? What happens when it repeats the same rhythm while traveling through space and time? The structures that describe this kind of change are the trigonometric functions. Trigonometric functions describe changes that repeat as they travel. The sine function oscillates continuously between -1 and +1. It repeats the same pattern every 2 pi. The interval between these repetitions is called the period, and the shift in the starting position of a wave is called its phase. But trigonometric functions describe more than a single wave. When multiple waves meet, their phases determine how they interact. They may reinforce one another, or they may cancel one another out. This phenomenon is called interference. When waves of particular frequencies overlap and produce a larger oscillation, the result is resonance. These structures appear across a remarkably wide range of phenomena, including sound, light, electromagnetic waves, communication systems, neural activity, and quantum mechanics. The important point is that a change occurring in one place does not remain confined to that location. It spreads into its surroundings. It encounters other changes, and through interaction, it gives rise to new states. The exponential function reveals the structure of growth. Trigonometric functions reveal the structures of periodicity, propagation, and interaction. By bringing these patterns together, we can identify 6 structures shared by the dynamic processes described by transcendental functions. The dynamic world described by transcendental functions can be organized into 6 structures. The first is change over time, in which the present state gives rise to the next. The second is self-amplification, in which an increase creates the conditions for further growth. The third is periodicity, in which a state returns again and again in a regular rhythm. The fourth is propagation, in which a local change spreads through its relationships with the surrounding environment. The fifth is interaction, in which multiple processes of change meet and alter one another. And the sixth is feedback, in which the result of a process returns to the mechanism that produced it, influencing what happens next. These 6 structures do not exist independently. A state changes. That change spreads. It interacts with other changes. The resulting state then becomes the condition for the next process, giving rise to further change. What transcendental functions describe is not a fixed and completed form. They describe a continuing process in which one state gives rise to another. And this structure does not exist only within mathematics. We can observe the same generative cycle in life, in nature, and even in the formation of the universe. What life and nature share is a simple but powerful principle. The result at one moment becomes the cause of the next change. A cell divides to produce new cells. Those new cells then become the agents of further division. In biological evolution, variations emerge through interaction with the environment. These differences are passed on to the next generation. Over time, their accumulation can lead to new traits and even new species. The same underlying process appears in population growth, the spread of infection, relationships among organisms within an ecosystem, and the formation of the large-scale structure of the universe. In each case, the present state helps determine what comes next. The sequence shown here represents this process. A state at time t interacts with its surroundings and becomes the next state. At time t+1, that new state then creates the conditions for the state that follows. Nature does not simply reveal a series of forms that were completed in advance. It is a continuous generative process. The result of each interaction becomes the cause of what happens next. allowing the system to update itself again and again. And this structure, in which each result becomes a new cause, appears not only in the natural world, it can also be found in human society, where it drives the creation of knowledge, language, and economic activity. In human society as well, what has already been created changes what can be created next, and how it can be created. New knowledge gives rise to new questions. Those questions can lead to research methods and discoveries that did not exist before. Language works in the same way. When new forms of expression are shared, new meanings emerge. These meanings change the way we think, and even the way we communicate. On social media, reactions to a single post can drive the next wave of distribution. As these reactions spread, they reshape relationships between people and change both the reach and the speed of information. In markets, expectations about the future influence prices and investment decisions. The results of those decisions then reshape the expectations that follow. What these processes share is that creation does not end when something has been produced. What is created changes the relationships around it. Those changing relationships update the capacity of people and society to create. And from that renewed capacity, the next act of creation begins. The future is not produced by individual elements alone. It emerges from the relationships among those elements, and from the recurring process through which those relationships are renewed. This brings us to a deeper question. Does something exist independently from the beginning? Or does it come into being, temporarily, through its relationships with everything around it? This question appears in many different traditions of thought and fields of research. Across different periods of history, the Buddhist concept of dependent origination holds that everything comes into being through its relationships with other things, and through the conditions that surround it. Process philosophy views the foundations of the world not as fixed substances, but as a continuous flow of events and change. The concept of autopoiesis describes life as a system that maintains itself by continually producing its own components. In complex systems, interactions among many elements can produce an overall order that is difficult to predict. The concept of emergence shows how properties that do not exist in any individual element can arise through the relationships among them. Each of these ideas comes from a different background and carries its own distinct meaning, yet they share an important perspective. They do not assume that separate things exist first, and only then enter into relationships. Instead, forms and functions emerge temporarily from ongoing relationships and change. From this perspective, existence is not a fixed object. It is a continuing process. Could intelligence be understood in the same way? Perhaps intelligence is not a fixed entity that stores a collection of completed answers. Perhaps it is a process that generates answers through relationships and context. From this perspective, the transition from classical artificial intelligence to modern artificial intelligence becomes much clearer. In a typical classical approach, humans define the rules in advance. The system is instructed to process information in the form of, if A, then B in principle. The same input receives the same predetermined treatment. The expected behaviors of the system are also specified beforehand. Modern generative artificial intelligence works differently. It learns the structures of relationships among words and concepts from enormous amounts of data. In response to the current context, an attention mechanism reorganizes which relationships the system should consider. It then assigns probabilities to the possible tokens that could come next. One token is selected. That token becomes part of the new context, changing the probabilities for the token that follows. When multiple artificial intelligence agents take on different roles, the output of one agent becomes part of the conditions for the next agent's decision. This can produce a coordinated process of generation. In such a system, it is impossible to specify every answer and every behavior in advance. Modern artificial intelligence is not a machine that simply retrieves completed sentences from storage. It is a system that constructs each answer in the moment, using learned relationships and the current context. So, through what process is that answer actually generated? One word at a time? Generation in a large language model, or LLM, is an iterative process in which each output becomes part of the conditions for what is generated next. First, the model uses the context accumulated so far to calculate a probability distribution across all the tokens that could come next. It then selects one token, based on that distribution and the chosen sampling method. The selected token is produced as output. At the same time, it is added to the original context. This updates the context. which in turn changes the probability distribution for the next token. The model calculates, it selects, it adds the token to the context, then it calculates again. Through this repeating cycle, text is generated one token at a time. For example, suppose the sentence, "It rained today," is followed by, "I forgot my umbrella." This makes an outcome such as, "My clothes got wet." More likely, once those words are added, the range of likely continuations changes again. A generated word is not simply a result, it becomes a new condition that changes what can be generated next. However, the model's learned weights are not updated during ordinary inference. What changes is the model's internal representation of the current context, along with the conditional probabilities assigned to the next possible tokens. But what does it actually mean for the internal representation of the same word to change depending on its context? At the center of this mechanism is attention. Consider the English word, bank. On its own, the word does not tell us whether it refers to a financial institution or the side of a river. In the phrase, financial bank, the relationship with the word financial receives greater attention. As a result, the model constructs a representation closer to the meaning of a financial institution. In the phrase, river bank, the relationship with the word river becomes stronger. The representation then shifts toward the meaning of land beside a river. Within the attention mechanism, each token is used to create a query, a key, and a value. The model compares queries with keys to calculate how much attention each element should receive. It then applies those attention weights to the values, combines the resulting information, and updates the representation of each token. In other words, the representation of a word is not treated as a fixed value in isolation. A context-dependent representation is constructed according to the words around it, and according to which relationships receive the greatest attention. A transformer does more than retrieve meanings from a fixed dictionary. By examining relationships within the current context, it constructs a representation of meaning suited to that specific moment. The expression, "a wave of meaning," is a metaphor for the way these relationships spread through the context. So, what happens when we extend this principle beyond relationships among words, and apply it to relationships among multiple forms of intelligence? What happens when the elements interacting with one another are artificial intelligence agents? In a system where multiple artificial intelligence agents work together, the intelligence of the whole is not determined simply by adding up the abilities of each individual agent. What matters is how the relationships among those agents change over time. This is known as relational dynamics. Each agent has different capabilities and takes on a role suited to the situation. Based on that role, the agent contributes knowledge and evaluates the results produced by others. Through this process, the strength of trust among the agents changes. Trust is not uniform. An agent may be highly trusted in one domain, but trusted only to a limited degree in another. These relationships of trust influence whose information receives the most attention, and which decisions are ultimately adopted. The results of those decisions then return to the system as feedback. Based on success or failure, the next assignment of roles may change. The sources of knowledge may change. The weights of trust may change. And the conditions for future decisions may change. This leads to a central idea in Chinoba: intelligence as relationship. From this perspective, intelligence is not only a fixed ability contained within an individual, it comes into being, and continues to change, through a recurring cycle in which relationships are constantly updated. But if the designers of such an artificial intelligence system cannot predict all of its behavior in advance, has that system become transcendental in the mathematical sense? At this point, we need to make an important distinction. In mathematics, the word transcendental has a precise definition. A transcendental number is a number that cannot be the solution to any algebraic equation with integer coefficients. The number e and the number pi are well-known examples. When we speak about artificial intelligence, however, we are describing a different kind of property. The behavior of an artificial intelligence system can change through context, environmental conditions, and interactions among multiple elements. As a result, it can be difficult for its designers to list every possible behavior in advance as a simple table of rules. Artificial intelligence systems are still implemented using finite code and a finite number of learned parameters. Therefore, the difficulty of predicting their behavior cannot be treated as mathematical transcendence. The connection between the two is not one of identity. It is a metaphor based on structural similarity. In a large language model, Each generated token changes the context for the token that follows. In a multi-agent system, the results of interactions can change roles, levels of trust, and the conditions for future decisions. In a self-improving system, evaluation results can feed back into the next process and influence the direction of future exploration. Artificial intelligence has not become transcendental in the mathematical sense, yet its behavior changes from one step to the next, shaped by its environment and by the history of its own generation. For this reason, it cannot be governed through a fixed table of outputs alone. The goal should not be to define every possible result in advance. What must be governed is the generative process itself, the process through which results emerge, and decisions are ultimately made. Traditional system design begins by defining specifications, translating them into rules, and producing predetermined outputs. Generative artificial intelligence works differently. Context, the model itself, and interactions with users or other agents combine to create multiple possible outputs. As a result, the same model can produce different responses in different contexts. A single error can also propagate through a chain of interactions, expanding its impact across the system. In a multi-agent system, the sequence of exchanges among agents can change the behavior of the system as a whole, and depending on the generation settings and execution conditions, the same input may not always produce a single, identical result. The number of possible states and combinations is also enormous. This makes it impractical to test every possibility in advance. But eliminating generation itself would also eliminate the value of generative artificial intelligence. The answer is not to predetermine every possible output. Instead, we must understand the entire process as a connected sequence. The input context, the information that was referenced, the interactions that took place, the decision that was selected, and the result that followed. The first step is to avoid treating content generated by artificial intelligence as if it were already a decision or an action. An artificial intelligence output is information that can support a decision. It is not yet the decision itself. Clearly separating these two is the starting point for governing the generative process. Artificial intelligence can generate proposals, hypotheses, estimates, classifications, risk assessments, and possible courses of action. These outputs can provide valuable information, but they do not, by themselves, constitute a decision. An artificial intelligence output is a signal passed into a decision-making process. To make a decision, we must first clarify the objective to be achieved and the current situation. We must then examine the evidence supporting the output and compare it with the policies that apply. Next, we define the boundary. This establishes the limits within which action is permitted. We then confirm the authority. This determines who has the power to make the decision. Depending on the level of risk, we introduce a human gate. This ensures that a person reviews and approves the decision when necessary. Finally, we establish responsibility. This makes clear who will be accountable for the outcome. Only after these conditions have been satisfied can a decision be formed. For this reason, an artificial intelligence output should never be connected directly to an action. Between output and action, there must be an explicit decision process. That process must verify the objective, the situation, the evidence, the applicable policies, the authority, the required approval, and the responsibility for the result. It must also preserve a continuous record. What happened? What did the artificial intelligence indicate? Which options were considered? Who approved the decision? And why was the action taken? The model that structures this flow of decision-making is called the decision trace model. The decision trace model is a framework for transforming generated signals into decisions that can be controlled and traced. The process consists of 6 stages. The first stage is event. This stage captures what has happened in the real world or within a system. The second stage is signal. This records what an artificial intelligence system or sensor detected, and what it proposed in response to the event. The third stage is decision. At this stage, multiple options and their supporting evidence are compared, and the selected course is made explicit. The fourth stage is boundary. Here, the proposed decision is evaluated against laws, policies, and risk criteria. This determines what is permitted and what is prohibited. If the required conditions are not satisfied, the process stops or is sent back for revision. When the importance or risk is high, the process moves to the fifth stage, the human gate. At this stage, a person may approve, reject, or modify the proposed decision. Only a decision that satisfies the required conditions can proceed to the sixth stage, action. The system records not only what action was taken, but also the decision, the approval, and the supporting evidence. Together, these records form the trace. The trace is more than an audit log used to establish responsibility after the fact. It also becomes an input for learning. The outcome of the action can be reviewed to identify problems and improve future decisions. The decision trace model does not simply record a decision and stop there. It creates a continuous cycle in which the record of one decision becomes an input into the next. In the decision trace model, the trace is more than an audit log that preserves the past. When a decision leads to an action, it produces an actual outcome. That outcome, together with the process that led to it, is structured as a trace and examined through evaluation. The evaluation asks more than whether the action succeeded or failed. Which signals were useful? Were any important options overlooked? Which boundaries allowed the action to proceed? And which ones stopped it? Were the human gate and its approval conditions placed appropriately? Through which relationships did any failure propagate? And did the final outcome meet the original expectations? By evaluating these questions, we can improve future decisions. We can improve the selection of signals. We can improve the range of options considered. We can refine the boundary conditions. And we can improve the way humans participate in the process. In this context, learning does not necessarily mean automatically updating the weights of an artificial intelligence model. It means improving the entire decision-making system, including its rules, workflows, roles, and evaluation criteria. The decision trace model, or DTM, is not a mechanism for defining generative behavior once and then fixing it permanently. It is an infrastructure for continuously examining the cycle of decisions and outcomes, and using what is learned to improve the decisions that follow. Through this cycle, predictions and proposals generated by artificial intelligence can be connected to decisions that function responsibly within society. We have followed a single path, from transcendental numbers, to transcendental functions, to generative artificial intelligence, and finally to the decision trace model. Transcendental numbers revealed a world beyond what can be captured by algebraic equations. Transcendental functions gave mathematics the power to describe a changing world, a world of growth, waves, cycles, and interactions. Modern artificial intelligence does not simply retrieve fixed answers. It generates each output step by step, through context and relationships. In a multi-agent system, the behavior of the whole is shaped not only by the abilities of individual agents, but also by their roles, their levels of trust, and their relationships to knowledge. This is why we must govern the generative process, instead of attempting to fix every possible output in advance. And we must never forget one essential distinction. What artificial intelligence generates is a signal. That signal is not yet a decision. To transform a signal into a decision that can function responsibly within society, we need clear boundaries, human gates, responsibility, and evidence. As artificial intelligence becomes more generative, model performance alone is no longer enough. What will determine the value and reliability of artificial intelligence is the structure of its decision-making. What is permitted? Where must the process stop? Who makes the decision? Who takes responsibility? And what evidence is preserved? In the age of generative artificial intelligence, the goal is not only to predict more, it is to transform generated possibilities into decisions that are explainable, accountable, and responsible. The governance foundation for achieving this is the decision trace model. Thank you for listening.